Nuclear transformations, fission, and fusion. This part of the chapter is just a very brief overview about the importance of nuclear transformations. Much of what you will have to do on the exam will probably be writing equations, identifying the kind of radiation that's produced, and doing half-life problems. So this is just some information for your background knowledge. Nuclear transformations, why are they important? Well, this is when things can become other things. Remember the law of conservation of mass and the law of conservation of energy. That means that we can't suddenly produce something out of nothing. We can't produce energy without having initial stored energy there. But nuclear reactions are totally different. In fact, we can change one atom into another, and by breaking a nucleus apart, we can actually produce more energy than it took into breaking that atom's nucleus, therefore releasing huge amounts of energy. So it goes against these laws of conservation of whatever that we had earlier in our science careers. So here's an example when you can take aluminum, bombard it with an alpha particle, and you can see we're producing phosphorus, something that's totally different with totally different properties. It also here releases a neutron. Here's californium becoming seaborgonium by the bombardment with oxygen. So in radioactivity, when an atom is becoming stable and decomposing and producing these particles, alpha, beta, gamma, etc., how do we measure that radiation? And that is with a substance or a machine called a Geiger counter. This usually is something that can detect the amount of millirems, that's a unit of radiation, coming off of the surface of the ground or in the air. And a scintillation counter is also a similar device. These are devices that can measure radioactive levels. What's the importance of radioactivity? Well, carbon-14 dating has nothing to do with dating, and it has nothing to do with being age 14 and being able to date, but it has to do with putting a date on old substances, those things that are organic in nature, such as wood and cloth. If you take art history or are interested in art at all, you know that sometimes very ancient paintings might have been painted on wood, and these substances may come from, before medieval times or after, but we don't know. But the scientists can tell by taking a sample of that and comparing a sample of the carbon-14 that still remains in the wood to what it should have had it been from the 1300s or before. So that's how we are able to use these kinds of radioactive isotopes to our benefit. And it really is based on the carbon-12 to carbon-14 ratio. So as carbon-14 decomposes to become stable, carbon-12, it takes a certain number of years for that to happen. And we can check and see what that ratio is and then determine the age of that artifact. Other things that we can use to our benefit, well, radioactive nuclides that are introduced into organisms in food or drugs and whose pathways can be traced by monitoring their radioactivity is one way to do that. So there are tests. If you have some stomach trouble, for example, you might go to the doctor and they would do a series called a GI series. So the gastrointestinal series, as it's called, would be where you would actually drink a liquid that has some radioactive material in it, usually barium. So you drink what looks like kind of a white milkshake, you drink it down, it has the radioactive material in it, and the reason for that is then if your body is put behind a machine or in a machine that can sense that radioactive isotopes movement through your stomach and your intestines and so forth, then there might not be a need for some surgery, because they can see if there's a blockage or if you're having some sort of tummy trouble as a result of the information that is received from this radioactive isotope as it passes through your body. Some people would argue that you should stay away from radiation, of course, but some people might also argue that to do extensive surgery that isn't very necessary could also put people at risk. So you have to weigh the risks and benefits to determine, obviously, if that kind of thing is appropriate at a particular time. Here are some examples of nuclides that are used to study the human body. So iodine 131, area of the body studied, thyroid. Again, these are just pieces of information for you. You definitely don't have to know any of this information, but it's just kind of interesting to see the half-life of these materials as it makes it through your body, if you're trying to look at red blood cells or bones or lungs, etc. These are their half-lives, and these are the radio tracers, as they're called, that can help scientists and doctors treat people with illness more accurately. Another concept of thermodynamic stability of the nucleus is the relationship between energy and mass. As Albert Einstein found, there is that relationship, which you know as E equals mc squared. Delta M is the mass defect. Delta E is the change in energy. And if delta E is negative, or exothermic, mass is lost from the system. And in fact, we can actually convert mass into energy with this kind of relationship, which is something that, according to law of conservation of mass and law of conservation of energy, we did not think was possible. But with nuclear chemistry, these things become possibilities. And the last section of this chapter deals with two concepts, fission and fusion. These are ways of thinking about the nucleus. Fusion, as the name suggests, I think of fusing things together, combining two light nuclei to form a heavier, more stable nucleus. That's what fusion is. Here's an example of one. Helium and hydrogen form a more stable isotope of helium. You might recognize that as an alpha particle, 4,2 helium, and 1e. That's a positron. The other, fission, if you think of fizzing, like fizzing apart, fission is splitting heavy nucleus into two nuclei with smaller mass numbers. Oftentimes those mass numbers are more stable, so some fission is an opportunity to break a larger atom apart to form more stable byproducts. In fact, fission was founded in the 1930s when uranium-235, which you see right here, was bombarded with neutrons. This reaction produces about 2 times 10 to the 13 joules of energy per mole of uranium, which doesn't sound like a lot, but does produce a huge amount of energy. It's actually 26 million times more energy than burning methane. So think of traditional methods of producing heat. You know, you burn something, like a Bunsen burner. We produce heat by burning some methane gas or some gas. It produces energy for us. But this reaction that you see here produces 26 million times more energy than that per mole. Huge amounts of energy. And that's the reason we want to harness the energy of fission, uranium being bombarded with neutrons, to then use that energy to do useful work. And in class we might be able to see a little bit of the positive nature of nuclear energy and the negative when it's not, the byproducts are not housed properly, or there's a core meltdown. But in general, that's what a fission reaction is. What are the biological effects of radiation? Well, it depends on the energy of the radiation, how much energy was there, and how penetrating the radiation is. I think I mentioned earlier that alpha particles are not particularly penetrating, so as long as I have my clothes on, I'm good to go. That would certainly not stop the effect of gamma radiation. Ionizing ability of the radiation. So gamma radiation is ionizing radiation. Other kinds of radiation we're familiar with every day. Things like microwaves and radio waves. These are forms of radiation as well. They're part of the electromagnetic spectrum. The visible spectrum is part of that as well. Energy coming from the sun. The low energy waves are non-ionizing radiation, but the high energy, the ultraviolet rays, those damaging rays from the sun, and gamma rays are ionizing. And so if it's ionizing radiation, it can have the potential to do cellular damage. And of course, the effects of radiation depends on the chemical properties of the source itself.